When I taught science to middle school kids, they would often ask me to explain relativity, and while they were unequipped to deal with the mathematical details, I found ways to explain it in ways they could understand. I always started with the basics. I would start by explaining why they call it relativity in the first place, pointing out what one observes is relative to one's frame of reference, or to put it in language they can understand, what you see depends on your vantage point. For example, for my frame of reference here, sitting in my house in Colorado, I appear to be motionless. But from the frame of reference, from the vantage point of the moon, I would appear to be rotating to the east at 500 miles an hour as the Earth rotates. Next, I would point out that there is no absolute frame of reference. No observing place is special. There's nothing special about my frame of reference here on the Earth. There's nothing special about a frame of reference on the moon, because an observer on Pluto could look back and see the Earth and the moon going around the sun in that direction at 66,000 miles an hour. Pluto is not a special observing place because somebody outside the galaxy on Andromeda, for example, would see the sun spinning with the entire Milky Way galaxy at 600,000 miles an hour, and on and on and on. Another important concept for students to understand is that all of the laws of nature are the same in all uniformly moving frames of reference. In other words, nothing changes if the motion is steady. It's pretty easy to demonstrate from my motionless frame of reference, which is considered to be uniformly moving. And in that frame of reference, I have no trouble tossing a ball up and down. Now let's see what happens if I walk across the room at a uniform speed, tossing the ball up and down. According to what I just told you, all the laws of nature are the same in all uniformly moving frames of reference, so I should have no trouble tossing the ball up and down and catching it. Now, if my motion is not uniform, if I speed up or slow down, all bets are off. So what I've explained so far is pretty intuitive even to middle schoolers. What you see depends on your vantage point. There is no special or privileged vantage point. And if you're moving at a steady rate, you can pretty much do the same things that you can do sitting in your living room. Kids know this from riding in cars and in airplanes. They know that it's very similar to sitting in their living room until the car speeds up or slows down. So what's the big deal then with relativity? Why did Einstein become so famous for it? There's got to be more to it than what I've explained so far. Indeed there is. If you ask middle schoolers at what speed a ball would hit the wall if they were running towards the wall at 10 miles an hour and threw a ball at 10 miles an hour, most would correctly say 20 miles an hour. Then you explain that in the late 1800s they were pretty much doing the same experiments with light, and they were astonished to learn that it didn't matter if the light was being emitted by an object moving away from the observer or towards the observer or sideways to the observer. The speed of light was always the same. From those observations, it had to be concluded that the speed of light was a universal constant, but it was very difficult for scientists to explain. This set the stage for young Albert Einstein to explain this dilemma in 1905. Speed is simply a measure of distance divided by time. For example, if somebody runs 100 meters in 9.5 seconds, their speed is 10.3 meters per second. But what happens if speed, like the speed of light, is a constant? Here's where it finally gets weird and counterintuitive. In order to maintain a constant speed of light, if distance changes, then the measurement of time must change as well. Time must slow down. Kids always want to know if time really slows down or just appears to slow down from an observer in another frame of reference. Time really does slow down. They would never know it because the rule that all the laws of physics are the same in all uniformly moving frames of reference applies. Their watch would slow down, their heart rate would slow down, everything would slow down by the same amount, so they would never be able to detect that. Someone in another frame of reference would be able to measure it if they had an accurate enough atomic clock, or if they were going at some significant fraction of the speed of light. Of course, there is more to Einstein's special theory of relativity than what's in this video, including his famous equation E equals mc squared, but that's for another video. And by the way, this theory, this part of his theory, is called the special theory of relativity because it restricts itself to uniformly moving frames of reference. Einstein was well aware of the limitation of that. In the real world, things speed up, they slow down. So he spent the next 10 years coming up with a theory that encompasses all frames of reference. And he would succeed, and that would become his theory of gravity, his general theory of relativity. Nothing in this video is beyond the comprehension of most middle schoolers, but it's just mysterious enough and counterintuitive enough to spark their interest. So I encourage middle school teachers to dive into this with them because they're interested.